No me retraso más y los dejo con Fabrizio.
Muchas gracias. Es un gran honor para mí estar aquí otra vez en Guanajuato, después de 2 o 3 que no me recuerdo, pero otra vez amigos como Víctor, Andrés y otro, Leticia y otro. Y sí, yo prefiero hablar en inglés porque hablar en inglés me sale más natural. Hablar en italiano y en español es más difícil. El primero es lo que dice mi esposo, ¿okay? Que no siempre hablo bien en italiano. Eso es. Entonces, no, en general no utilizo el micrófono, pero después de 1 hora y media de curso prefiero utilizar el micrófono. La charla de hoy, sorry, inglés. The talk of today is about my opinions or my small ideas about what is the future of stochastic modeling when in the era of artificial intelligence and machine learning. The point is that it's a matter of I started working 40+ years ago, and those days it was just stochastic modeling, and now the people in artificial intelligence and machine learning are kicking me out, people like me out of business because of this. So I'm trying somehow to defend our category of people who are working on stochastic modeling. But of course, not in a silly way. So it's important also to cooperate, to think about what is useful for people in machine learning, what is useful also for people in stochastic modeling. And the talk today will have some mathematics, some statistics, but I try to keep it not too deep on that because I was told there will be people also are not statistician or probabilist. So what I'm going to talk about is just to mention first some quotes, and then I will talk about some ideas. I will tell you where they're coming from, and then 5 examples of models in which I've been working. Somehow, some of them also related to cooperation between stochastic modeling and artificial intelligence and machine learning, and then some concluding remarks. So these are some quotes. You can see very different opinions about them. So the first one is from a computer scientist who says, we can stop looking for models. We can analyze the data without hypothesis about what it might show. We can throw the numbers into the biggest computing clusters the world has ever seen and let statistical algorithms find patterns where science cannot. So this is one opinion. Then there is the most famous citation in statistics by George Box. All models are wrong, but some are useful. Then there is a distorted, that's my biased opinion, by the way, by Peter Norvig, who is a computer scientist. All models are wrong, and increasingly you can succeed without them. And then there is the last quote is from a very famous Italian physicist, Carlo Rovelli, and this has been translated from Italian by this co-author of the paper that you will see pretty soon, Cesare Secchi, which says the following: the goal of science is not to make predictions. It is also offering an image of reality, a conceptual framework for thinking about things. This ambition has made scientific thinking effective. If the goal of science were only predictions, Copernicus would have not discovered anything compared to Ptolemy. His astronomical predictions were no better than Ptolemy's, but Copernicus found the key to rethink everything and understand better. You can see there are completely different opinions about what's going on, what we should do. Now, there are some quotes here at the end, which are taken from this paper. Is there a future for stochastic modeling in business industry in the era of machine learning and artificial intelligence? I've been editor-in-chief of this journal, Apply Stochastic Models in Business Industry, for 17 years, long life. And that was my final gift to the journal. I asked a lot of friends of my people who have cooperated, from David Banks to this guy, IBM, to write something. So it's a collective paper in which every one of these people, or sometimes together, wrote what they think about the question I raised. It's in the title of the paper. So the point is that where are we now? Well, respect also when I was younger, So the advances in analytics due to AI, ML, or deep learning have changed a lot the approach to data analysis. So the question, as I said, I've been for 17 years editor-in-chief of this journal, and I saw changes in the kind of paper that we were receiving. At the very beginning, were essentially just the traditional stochastic models, and then at the end, a lot using deep learning, machine learning, neural networks, and so on and so on. So I have this question that is behind this talk. The point is that this talk is not against artificial intelligence. It's not against learning, not at all. But I recognize the importance, the effectiveness of them. But I would try to think, what can we do now? I define myself as a stochastic model. What can we do now in this new context? Still an opportunity for us. The answer for me is yes, of course. Not against, but together with, sorry, I know that I'm making a lot of mess. And also now, so the point is that this is the idea. So a proper methodology for assessing the right balance between purely data-driven empirical methods, physics-based models, and probabilistic stochastic models is requiring further development. So we need to combine all the methods provided by physics, biology, engineering, medicine, or what else, methods of machine learning from stochastic models to get a data-driven knowledge. That is the point. So the point is that our stochastic models sometimes are better to quantify uncertainty with respect to machine learning. So this is an important aspect, because if you want to make a decision making in the real world, we have also not only to make some predictions. We don't just need a number. We need also to know how much we trust this number. What could happen if something else is going to happen? Also, there is an issue of explainability. I am aware of Shapley-Walius work of explainable artificial intelligence. A lot of work has been done, and some achievement has been obtained, and that is really important. Still, the stochastic models are better from this point of view. Also, this is the risk. So when you have to build trust, for example, in domains like healthcare and finance, is very important. Also, there is an issue of sample size. Well, if you have a lot of data, well, machine learning may be fine. But sometimes you don't have many data. My typical example is about failures of nuclear plants. I use also that to justify the use of Bayesian statistics. A lot of knowledge, very few data. We can use Bayesian statistics and the models that we have. Now, so the point is, if you are going to predict the occurrence of future event, for example, this, as I said, these are just quotes taken by the contribution of the people to this cooperative paper. So if the question is predicting the occurrence of a future events, like the future conditional mean of stochastic process, if there are a lot of data, then with many variables, then the machine learning methods might be a first choice. But sometimes we're not only interested in making prediction, but want to understand what is driving what has led to this data. So we are interested in the data generating process. And this is what we would like to do. So we know that all the models are approximation, but we would try to get insight about why the data are behaving in this way. But there are also some points, some aspect of statistics which is difficult to address by using machine learning. A typical example comes from the design experiment when you're talking about randomization, replication, and blocking, or when you're talking about sample surveys, because there is bias like selection, response, no response. That is something which is very important. So there are a lot of aspects still, I will see some others, in which maybe machine learning has to do still a lot. So this is the typical example, is the survival analysis. And survival analysis has been developed with end-of sensor and truncated observation. And there are works about the use of deep learning, especially exploiting unstructured or high-dimensional data, such images, text, omics. But if you go to this website, you will see that there does not exist much about this kind of observation. So this is an example in which stochastic model for the moment is doing better. Also, someone else is mentioning that the corporate probability of default is important. I'm not an expert in this one. So an algorithm, ML algorithm, would be useful in identifying which customers are more liable to default. But where you're interested in the overall probability of default, then you have to talk about population parameter. And then, in this case, stochastic modeling may be useful. Now I'm going to present 5. Yes.
Yes, excuse me. My English isn't very good. Can you please explain what omics means?
Genomics or omics. Yeah, genomics, all this kind of areas in which now we have a lot of data. I think there are others which are called omics, but genomics is the one we have a lot of data about genes, DNA, and you have a lot of data, and this is the science of applying quantitative methods to genetics, for example. This is the omics. Okay. This is jargon. Okay. Of course. Now, I'm going to talk about 5 works of mine in which you will see sometimes the importance of stochastic modeling, and sometimes also the cooperation among them. So, well, these are the title. Now let's see what will. Let's start with the first one. Of course, the other direction. So, healthcare frauds. And here, what I'm going to present are very, very simple tools, typical part of descriptive statistics, but which, and also about data visualization, which could be useful without any machine learning stuff here. So what I'm talking about, sometimes this is a problem, it's working with people in the United States where this is a big problem, the healthcare frauds. In the European Union where I live is a less different problem because we have an health system which is definitely better than the one in the United States, which is it's a national health system. It is more difficult to have the frauds, at least in this kind of problems. So here the issue is the following. Maybe there are some providers which are charging too much for some exams, or are charging for exams which are not necessary, but they give them a lot of money out of that. There are sort of abuse, waste, and fraud. And statisticians can contribute not in finding frauds, but possible frauds, anomalies we call it in our paper, because we don't have the expertise to detect if are frauds or not. There should be someone who has knowledge about all these medical procedures, so we need some auditors in going to do that. But I'm going to present you some models in which we can try to find some anomalous behavior of providers. So an assumption of this is the following. There is a group of medical doctors which we think are homogeneous in terms of patients, in terms of experience, practice, and so on. And then we are interested in knowing if someone apart from this group is behaving in a very different way with respect to the others, in terms of how much they charge and the kind of prescriptions that they are providing. And the tool they started with is the Lorenz curve. I don't know if you are aware of this one. The Lorenz curve is a tool, goes back 1905 to the American economist Lorenz. And it is something which is telling us about the spread of the wealth in a population. So let's suppose there are n people in a population, and let's the wealth or income of these people, let's be x sub I, and then we order this one with x1, xn, and then we plot a curve like the one you can see here, done in this way. On the x-axis, we plot the proportion of the population, starting from the poorest, the first two poorest, the third three poorest, and so on. And on the y-axis, we plot the percentages of wealth they have. We suppose the percentage of wealth is summing up to 1, or we divide in this way. So here we have k over n, which is, in this case, the number of elements, of individuals K are the first K poorest. This SN is the total wealth of the population. SK is the total wealth of the K poorest. Let's see the following. Let's suppose we have a population made of 3 people, and let's suppose that we have another population, a population in which one has 10% of the wealth, one is 30%, and one is 60%. Then there is also this other example. So how do we build this curve? So we start with the poorest, 0.1, which corresponds to 1/3 of the population. So we put 0.1 here, 1/3 here. What are the 2 poorest? These 2. The sum of them is 0.4. They represent 2/3 of the population, so 2/3 here, 0.4 here. And we connect. We get a curve which is convex, increasing between 0, 0, 1, 1. What would be the curve corresponding to an equal distribution of wealth? Would be the straight line. How do we measure the discrepancy, the inequality? Well, there are different indices. In particular, we use 2 of them, due both to Italian statisticians, 1914, 1915. One is the so-called Gini. Gini was the founder of the Italian Statistical Society, of the first Department of Statistics of the Italian National Statistical Office, Corrado Gini, and which is twice the area between this straight line and this one. It's a number between 0 and 1. The other index, due to Gaetano Pietra, is the maximum distance between this curve and the other curve, which might go up to 1, because if I get something like this, goes up to 1. So these are somehow summarizing indices of the inequality. But we can think in terms also of probability. In terms of probability, what is the Lorentz curve? It's a comparison between a discrete distribution over n points, 3 in this case, with respect to uniform distribution over the same 3 points. Now there are some generalization called concentration function. In particular, I've been working on one due to 2 other Italian statisticians, Eugenio Regazzini and Donato Michele Cifarelli, in which it is about the comparisons of 2 probability measures on the same measurable space, omega and f. It's called concentration function. We did a lot of work on them, also very sophisticated one, like building neighbors of probability measure by using the concentration function. But what you will see here is very basic use of this notion. So instead of comparing a discrete distribution with respect to uniform, I'm going to compare 2 discrete distributions. So that will be the change. And how do we do that? Well, I'm going in this way. So there are some outcomes. These are the outcomes, x1, xn. In our problem in healthcare is the percentages of prescription by doctors, percentages of X-ray, blood test, and so on. These are the prescriptions, blood test, X-ray, and so on. What we are interested are the percentages by the doctors in the group and the particular doctor. I told you the goal is to see if a particular doctor is behaving like the others to the group of which he's supposed to belong to. So here we have the following. This are the probabilities, but you can think also the probability, the percentages of X-ray, blood test, and so on given by a medical doctor. These are another probability, discrete probability, which you can think of the percentages given by the group of X-ray, blood test, and so on. How do we build, in this case, the curve? Because we are going to get a similar curve. We do the following. We take the likelihood ratio between the 2 probabilities for each I, and then we order based on this R. And we build a curve in this way. And I don't have the picture here. I usually have a picture showing it, but the idea would be the same. On the x-axis, we put the QI corresponding to this order. On the y-axis, we put the PI. You will see an example pretty soon with real data. So we got some data from the United States when they were still available. I don't think now they are available for various reasons. We have a group of 30 medical doctors in diagnostic radiology in Vermont. and we have billings, or percentage of the billings for 61 prescribed services, which are including all of this. We are interested in two doctors, in particular in the doctor MD1. So I make the hypothesis the doctors belongs to a homogeneous group. Of course, this is a very simplifying assumption. And we are looking at the likelihood ratio. For example, we have this one for the X-ray exam of abdomen is 9.65. What does it mean, 9.65? It means that this person is giving prescription for this kind of exam more than 9 times that the group he belongs or she belongs to. And the point is that it refers to almost 1/5 of his charges. So that's something which may be very, very strange. But then when we look at the concentration function, here it is let's call it is concentration function, is this one. It is one of these simple tools that one can present to a practitioner, and a practitioner can read from this the following. This is equal to 0 up to 0.5. What does it mean? It means that this medical doctor is not prescribing exams which corresponds to 50% of the exam prescribed by the others. And then there is this huge jump here, which corresponds to the ones which is giving and the other people are not giving. Here are the values of the Gini index and the Pietra. So this is something based on probability, and provides very simple tools. The Pietra index, we did for all the 30 doctors, we computed the Pietra index. You can see the Pietra index, when it's close to 0, it means a lot of similarity with the group. When it's far from 0, there will be some differences. So you can see all of this which are here probably are medical doctors which are not behaving like the others. Maybe it's a waste, an abuse, fraud, or simply it was wrong to put them in this homogeneous group. They maybe have to be removed because there may be some difference that it was not detected earlier. So the final one, I think it is the final slide, is about the Gini index for this kind of data from Medicare Part D in New Hampshire over 5 years, very interested in opioids. And we consider the Gini index over 5 years with respect to standard deviation for all the medical doctors. Here you can see the mean, and here you can see the standard deviation. How do we read this kind of plot? We read in this way. Those which are here have 0, both of them. That means they behave like the other doctor, the group, for all the 5 years. The ones which are here behaved very differently from the group for all the 5 years. This, for example, this one was very different with respect to group in 2013, but then very similar in 2017. And here, before I forget, because I was planning to say at the very end, this is here you cannot see, but there is an example of cooperation between artificial machine learning and our stochastic model. Because to analyze this data, we had zillions of data. What we did, we applied structural topic modeling. We extracted a lot of information from this by using machine learning tools, and we analyzed with this approach after this processing. Now, integrated pest management. This is a Lotka Volterra model. By the way, Vito Volterra was the guy who created my institution in 1923. He was the first president of the National Research Council of Italy, but it did not last much. The problem was very simple. We had the fascist government. He was not a fascist. And also, he was Jewish. That gave him other problems later on in his life. And that Volterra was replaced by Guglielmo Marconi. So that is the kind of people who have been president of my institution. Okay? So Lotka Volterra model is something like this. Why we were interested in this one? This is cooperation with biologists and also a colleague of mine who is an applied probabilist who got her job. It was in the committee. She said, I don't like statistics, even less Bayesian statistics. She was in front of 3 Bayesian statisticians, but nonetheless, we hired her because she's very brilliant. And so that's it. So this was about some strawberry field in Italy, in Sicily, and there was animal, which is called Tetranicus urtice, which was eating these strawberries, and they put this other animal, Phytocelius persimilis, which was eating the first animal. So it's so-called integrated pest management. So this is a model which we can read in some way. So we have a normalized mass between 0 and 1 of the prey. This is the increase at time t. This is the increase of the normalized mass of the predator. And then here we have this formulation with respect to increase of time. This is R, which is the specific growth rate of the prey. XT is its mass. But then there is this quantity which is somehow reducing it. Because when it increases too much, there are not enough strawberries for everyone. So when it increases too much, it has to go down. And then here there is the interaction between the two animals. And this is the skill of the predator to capturing the prey. And here we have, again, the skill of the predator to kill the prey, are related also to the specific production rate of the predator. And this is the fact that there are some loss rate of predator for different reasons, maybe predator of the predator. So you can see this is a stochastic models in which all the parameters have an interpretation. They correspond to reality in some way, at least as simplification. But then what we did was also this QT. So this is a differential equation. We did a stochastic differential equation. First introduced the following. QT is equal to Q naught plus sigma CT, which is a white noise. But then at the end of the day, the model became more and more complex because we had to add something else. So the first one, the QT before, gave rise to this Wiener process about demographic stochasticity due to variability population growth rates. But then for mathematical reasons and also for biological reasons, we added another Wiener process, which is affecting the increase, this was affecting the interaction. This is affecting all of them separately. We consider the same Wiener process, but with different weights. But also that was not enough because our masses were between 0 and 1, but we need to do something in which we could allow to go to minus infinity to plus infinity. How do we deal with this one? We consider a function which is essentially an approximation of the indicator function of 0, 1, but that is something like this and then goes down in a way which is continuous differentiable and Lipschitz. So we add this function. So here you can see a model which became a stochastic model, and now you can see the result. We use the Bayesian approach, and this is the Bayesian the results in terms of these are the asterisks are the data. And these are the curve of one cycle. So you can see the prey, which goes up, the predator at this point here is 0. I'll come back to that later. And then this goes up, but then the prey goes down and the predator goes down after that. If you are a statistician, you will say it's a very bad estimation. If you are a biologist, you will say this is the best estimation I ever saw in my life with this kind of data. Okay, why? Because it's difficult to collect data. We are talking about animals which are very, very small. You can do the experiment in the laboratory, but these are data collected in the field. Because in laboratory, there are conditions which are not comparable to the one in the field. And collecting data is very difficult. An example is this 0, which is here. So that was what we got, and we do the Bayesian approach. But then in another model, we consider it's called Ivlev model. It's more complex to explain, but I will not do that. You can see here that we get very, very, very close to the real data. Here you can see something which is called related to latent data. What is the problem of this data? Well, we use a lot of Gaussianity to deal with this. There are the Wiener processes. The point is that data are quite far away from one from the other. There are not many. So we have to use the so-called Euler-Maruyama approximation, which works very well when the points are close. How can we get point closer? Well, we put some latent data in between. And we treat them as a parameter in a Bayesian framework. There is a lot of, is there a theorem telling how many latent data should we choose? No, of course. rule of thumb. But you can see by using latent data, we got something. Right? So this is an example in which we have a stochastic model, which is based, in which starts from reality. We try to mimic it, and then we get some result. Now, immigration queue. This is a job done with people in Brisbane. I've been for a while adjunct professor in Brisbane at Queensland University of Technology.
In the last example, what's the artificial intelligence tool?
No, nothing, no. This is old days, 2012. In those days, there was no artificial intelligence, okay? Just human intelligence. We were using that one. Now, we are moving a little bit further, immigration queue. Here, what is the following, the problem? This is a PhD dissertation by Anthony Ebert with his advisor, with some other people in Australia. So we have this data. The data that we got are for the airport in Brisbane, Australia. And we have the following. Airplanes which are arriving in different gates. These are the arrival time, A1, A2, and so on. This is the disembarkation time of each passengers. Here there are cameras recording the passage of the people. Then there is a time to go to the immigration area, going through the concourse. Here there is another camera counting the people are passing there. Here the people can choose somehow to go through a manual gate or a smart gate. Long time ago, I had to go through the manual. Now, thanks to an agreement between European Union and Australia, I can go through the smart gate. But that was depending mostly on the nationality. And here there is a times to be served, and then there is a camera here, camera here. Well, the point is, are we able to build a likelihood and then do an estimation here? No. Why? Because if I can follow each person along all the way, you will see I have models for all step of this path, but I cannot follow a person because a person who is recorded here, I don't keep track of this person here and there and there, but I have data. So what is the computational tool that Bayesians have developed? It's called approximate Bayesian computation. So this is something about computation related to stochastic models, this example. So usually we use, when I started, we used a pen to write the conjugate prior and posterior, but then we moved to Markov chain Monte Carlo. The point is that sometimes the likelihood is too costly to evaluate or impossible to evaluate. So there are methods called likelihood free, which like this one, ABC, which are doing the following. We are able to build a model for the problem if we could observe the behavior of the person. And what we are going to do is that we have these models. You will see later what I mean by this. We generate some values of the possible parameters from prior distribution. And then we are able to generate new synthetic data from this kind of density. We are able to generate new data. We have on one side the real data, on the other side we have the generated data. What we are going to do is the following. Compare the two of them. If they are close, then the parameter theta stars that I have generated is a good one. That means it belongs to the posterior distribution, at least the approximation of the posterior distribution. If the x that we obtain are different from the real y, then we discard this one. The point is that sometimes these x's are many, like in our cases. So what we are going to do is to consider just a sufficient statistic. Sorry, I knew that I'm touching something wrong. Okay, so what we are doing is sometimes we use some sufficient statistics of this data, and then we decide to accept or reject this one. This is a critical aspect. In our work, we did the following. We used this, which is called the maximum mean discrepancy. This is the formula. Use this one. And, well, this is just technicalities. But now I told you, we know everything about, if you want to build a model, about the behavior of one person. Because we have, once the airplane arrives to the gate, we have a gamma distribution for disembarkation times. Then we have a gamma distribution for the time to go to immigration control. Then we have a Bernoulli distribution for a person being national, Australian in this case, or foreigners. And then if, depending on the nationality, there is a Bernoulli distribution for selecting either smart or manual gate. Then there is an exponential distribution for service time for manual and one for the smart gates. So we are able to build the model. When I was telling you before, we can generate synthetic data. How we do that? We put some priors on the parameters of all of them, and we generate a disembarkation time, an immigration control, a time to the immigration control, and so on. And we get some data, and we compare them with the real data. For doing that, we had to develop also, especially Anthony, the student, was able to develop a very fast algorithm because you need to do a lot of computation, which is called QDC. You will see the slide later on about what we have. So here is an example with the data. We have 29 flights, more than 5,000 passengers. We now have some information on the flight, arrival time, distance from the gate to the immigration control, number of passengers, percentages of passengers, number of machines, smart gates, number of manual gates. These are the sort of data that we have. You can see the black ones are the passengers which are arriving at the terminal. And then this straight line, you have to read on the other case, are the time in which the plane arrived at the gate, and also depending on the color, how many Australians are there. So these are the kind of data. At 3 different times of the day, we have this data. And then we did our estimation. I'm not going to show that one, but I'm just showing a technique that we use to see if something is, our estimates are good. So we are going to do so-called posterior predictive intervals. Based on our data, we would say where should have been fallen our observation. You can see in red, well, you can see somehow in red our predictive interval 95%, and the data essentially are inside that. So this is a good idea about how we did. Also, we made some forecast prediction about future waiting time of the people for new passengers. But then we did also something, this was actually what I wanted the student to do at the beginning. He did more about simulation. But at the end, we did also something like this. It was about more decision analysis. So the point is this one. We have the possibility of using this tool as a decision support tool. Now you will see 3 plots. One is about the prediction for looking at just the planned flight schedule. But then there is some disruption. One of the flights, the second one, is delayed by 15 minutes. And this is a dramatic change about the waiting time and the queue at the immigration booth. Because the waiting time at 10:50 goes from 28 to 71 minutes, and the median queue length goes from 146 and to 363 passengers. And then the idea is what happens if we move 2 people to officers there, and then there is a decrease of the median waiting time for 41 and the queue to 319. And this is what we have. So these are the arrival times and the size also of the planes, or the number of passengers. This was what we should expect in terms of 95% of prediction intervals for waiting times. But then this one arrives later, and here you can see a huge change of this one. But then we move 2 officers to work at this time, and you can see a reduction on this. So this is about stochastic modeling and developing new computational tools. ABC has become very popular nowadays in the Bayesian framework.
So
now,
what about the selection of the sufficient?
that's really a tough issue, okay? It's really, really tough. Because we used this one, it was working. Other people were using me or what else. There are many vast distance, a lot It's a very one of the most critical aspects of this aspect. It's really a critical one. We proved empirically that our choice was working well. That is when I presented the prediction interval with the actual data. So again, there is no theorem here showing what is the best one. This is something that the people who are attending my course tomorrow will see. So this is just the repetita iuvant. I studied Latin, but this is the Latin that everyone has to know to make a good impression, okay? Repetita iuvant. So adversarial classification, this is my more recent interest. So we have this, now we are entering in area in which there is cooperation between decision analysis and machine learning. This is an area which is called adversarial machine learning. To this work, my contribution is more about decision analysis, and my junior co-authors are more on the machine learning part, adversarial machine learning part. So, but this is something which is very relevant. Classification. Classification is very important because it's a supervised learning method applying computer vision, genomics, scoring, spam detection, and many other aspects. It's a very important area, but there is an issue. Many people are looking for algorithms which are working better, faster, more precise. The point is that there are also people who are attacking. So cybersecurity is a typical word related to classification in this case. So how can we deal with people attacking in this kind and trying to make other people make wrong decisions? The typical example I make, spam messages, people trying to change them. I still have 7 minutes, perfect, more or less. And then what we are going to do is the following. We are doing this one. We are thinking of this problem. We have two types of objects, malicious and innocent, plus and minus. There is an attacker, which is, so, and then there are some features. This is a typical way in classifying. For example, if you want to classify if the person is going to pay back mortgage, it will be plus or minus, pays back or does not pay, depends on the features of this person. He has a home, she has not a home, she has a salary, he has not a salary, and stuff like this. And then this is the problem from the point of view of we are interested. So these are the y, which is the real value, plus minus. These are the features. And then we have to make a decision about y, if it was plus or minus. But then there is one person who is making an attack. So the idea is this one. There is this feature x. This attacker is changing into x prime. And then I have, so the defender, we call it defender, this one, is to make a decision. Will be it is plus or minus. There are involved utilities and probabilities. This is the formulation. I don't have the time to go too much this one, but the idea is this one. I am an expected utility maximizer. My opponent is an expected utility maximizer. To maximize my utility, I have to think about the possible attacks by the adversary. And I have to do the following. I change my at, I put the at of the attacker. I think of the problem for this attacker, solve the problem for this one, and then I decide what to do. Because here the issue is this one. I have to find the class which is maximizing my expected utility. So this is the utility when the true value is y, and I decide yc. And this is the problem of y when I observe x prime. And here I have to split in different cases. I have to consider also all the possible attacks by this person. Here I'm supposing this attacking only when there is a malicious. So this is the problem. What is the problem? I don't know this kind of attack. So what I'm going to do is the following. I'm thinking as the attacker, and then I solve his problem. And at the end of the day, I'm able to find what is his possible attacks. And the technique is essentially considering the following. I'm talking about decision analysis, not game theory. The major difference is that we don't know exactly what the attacker is going to do. In game theory, we are supposing that you know each other what we are doing. In this case, I have only some guesses. So I frame the problem in this way. So this is the problem for the attacker. how I'm able to find the optimal decision for this person? Well, I have an opinion about the utility of this person, about this probability that I make a classification wrong, and I generate from a random utility a value here, from a random probability a value here, and I solve this one. I repeat it many, many, many times. At the end of the day, with all this optimal solution here, I get an empirical distribution about the possible attacks, and this is our distribution. Just to show you an example, this is an example about data which are including spam messages, and there are all these messages, 54 relevant words, and we suppose, and they are or not in these messages, so 0 ones, and the attack might be insertion of one attack. We did the typical things in machine learning, in training, so 75% were used for training, 25% for test. We repeated this many times. We also modify some of these spam messages into changing one word, and we compared our method with the very famous one called naive Bayes, and we showed that our method was doing pretty well. So this is an example in which we have, on one side, decision analysis, on the other, machine learning. And to conclude, the final one is about gate data. I don't know if you know about wavelets. I think I have only 2 minutes. So these are wavelets. What we're going to do is the following. So let's forget about what wavelets are. We have this guide data, and people have been using what. So these are data to understand how the elder people are walking. So they found 13 characteristics. They collect a lot of data. What we have done was to combine machine learning with wavelets in our models about self-similarity. So fractional Brownian motion combined with this one by using wavelets. And we were able to improve so these are some features, we were able to improve the accuracy in our estimation, because with the gate traditional one, this was the accuracy. This was the standard method of estimating the Hz parameter of the fractional Brownian motion. We proposed the new one. You can see we are doing better. Just to conclude, so the point is that I'm not against machine learning, definitely. Important is that we have to somehow cooperate. We can learn a lot about machine learning. It can be useful for statistical models, as I said, in the example in which we did structural topic modeling. But also there is an issue about trying to learn, machine learners, about, for example, missing data, about uncertainty quantification. So also it's important to try different ways of solving problems and see what we can learn from each other. Also, it's not a completely different topic. Deep learning is a sequence of regression from the point of view of a statistician. So also there is an issue about whether there are a lot of data, there are not many data, what is better or other. So we can learn each other. And these are just the references about the papers that I mentioned. Thank you.
Muchas gracias, Fabrizio. Muy bonita conferencia. ¿Preguntas? ¿Comentarios? ¿Tienes una pregunta?
No, comentario.
I will add one comment to the conclusion. We should be able to recognize one solution is better than the other.
Yes.
I think that will really give us more understanding of the difference.
Yeah, no, I completely agree with you. Also, there are situations in which so far stochastic models are doing better in terms of uncertainty quantification, explainability. This is a sort of a stimulus for people in machine learning to improve these two aspects. And also for us, it's a sort of stimulus of learning about, to do so, for example, it's some processing of our data by using machine learning technique. So it also shows examples in which we improved respect to machine learning. Also, the adversarial machine learning area is a nice area of cooperation between these two approaches, which, as I said, they are not separate. There is a lot of intersection in the cooperation, possible cooperation.
¿Más preguntas? De tu último ejemplo, que fuiste muy rápido, pero es que no, ¿qué es gate, data?
Entonces
Sí,
puedo
habla un poquito más.
hablar de esto. Muchas gracias. Ok, regresamos. Ok. Ok, vamos aquí, empezar. Wavelets. Wavelets son una bases ortonormales para describir. Sorry. It's a basis to describe functions, and with this property, the integral of this function phi is zero. That means it's a wave, and the integral of the square is equal to 1. It's a small wave. That's why it's called wavelets. The most famous one is the R wavelets, which goes back to 1910. It was not called wavelet in those days. Every continuous function in 0, 1 can be represented in this way. Just to show something for you. So this is the typical way of R wavelets, is between 0 and 1. So the first one is equal to 1 between 0, 1 half, and equal to -1 here. Then again between 0, 1, the next one, this is between 0, 1/4, and from 1/4 and 1 half. Again, the integral is 0, the integral of the square is 1, and then there is the other one. And then there are 4 here. And then there are 8, 16, and so on. There are a lot of coefficients. What we can see for the fraction Brownian motion is, which has this property, is very known. The coefficients of when there is a self-similar signal have this property. The expected value of the wavelet coefficient, because, go back to this one. These are the wavelet bases, but then to express a function, you need to multiply each one of them for a coefficient. And then this coefficient, this property, somehow related to the R parameter, and then there is the energy, the sum over at one level. And then there was a way of computing this H. And we proposed a different one. I'm not entering in detail this one, but we proposed another one. And now we have this data, which are about elder people who we want to assess the functional of these people who might have fallen in the past, to see how the gait is in Italiano is andatura, the way they walk, the way in which they walk. And we have some data. There are some tests like this one, which is 4 meters at usual speed. Another is raising from a chair, walking 3 meters, turning, returning, and sitting back. And then they put, so this data not collected by us, they put in some tool on the shoes so that they could walk for 30 minutes. They collected some data. And these data here are the ones which, we found they are somehow self-similar. So there are this kind of features which were extracted by the people who did analyze this data. There are different people who analyze this data. And then what we did was the following. We considered the Earth exponent for these 2 measurements done by the people working, and we compared our method with other 7 methods in typical in machine learning, and we did the following. For each one of them, we did a sequential forward selection. So we are adding one feature at a time based on some selection, was sort of cross-score validation of 5, something like that. And then after that, we decided to put all the 6 asked exponent, and we were able to find, here you cannot see what are the final choices, but then because it's just in the paper, but here you can see that we were able to improve the classification in this case. So that was another example of cooperation between modeling and others.
Excellent, perfect, yeah. Perfect. Also, just a last comment, if you have one, about putting priors on the parameters of a neural network and doing the Bayesian analysis of that. If there's a research area that, but
okay.
I just want your opinion.
Well, in this paper that is here. Okay, this paper, people wrote a lot of interesting stuff. My rubbish, I had 3 points in my rubbish. One of them was about Bayesian statistics. One of the major issues about Bayesian statistics nowadays is that we are not able to specify prior distribution when we are dealing with model problems which have thousands of parameters. My question is, there will be a day in which you can use artificial intelligence to gather information all around the world so that we will be able to write proper prior distribution for this 1,000 parameters or not? In principle, it may be possible, but don't trust artificial intelligence. The other day, I got a message from one person, and I checked who this person was. It was someone working as a job in building in my hometown, Reggio Emilia, and I went to artificial intelligence and said, he's a psychologist in Reggio Emilia. The point is that if you go in the network, you will see a psychologist in Milano and a builder in Reggio Emilia. So you put together. So don't trust artificial intelligence too much.
Okay.
So just wondering, like you mentioned that now many papers on artificial intelligence or machine learning are in this journal.
Yes.
So what is the percentage nowadays? So what's the editorial policy when you receive such kind of papers nowadays?
Okay. I am no more editor-in-chief since July 2024, but my policy was to look at the quality of the papers. It was not, we were not rejecting because it was machine learning. If it was a sound machine learning paper, we were accepting it. So there are. And now probably the new editor-in-chief, Nalini Ravishankar from Connecticut, is doing even more than what Louis did. I was rejecting papers which were just slight changes of existing papers, rejecting papers with not sound mathematics behind, but machine learning has never been a reason to reject a paper.
And the percentage?
I don't remember. I know that they rejected a lot of papers, but it was all across the possible approaches, okay?
¿Alguna otra pregunta? Bueno, muy bien. Muchas gracias. Le damos las gracias a Fabrizio. Antes de que se vayan, de parte del director que no pudo venir, un reconocimiento.
Muchas gracias.
Sí, y un regalo del SIAM.
Oh, muchas gracias.